Anybody have any questions before we do so? Please go ahead and chat me your first and last name too, if you haven't done so already. All right, so when we last met, we were working in chapter five. I had quickly went over a few examples of friction. I then did a derivation of the centripetal acceleration. That's actually an extra credit problem you can work on your own, by the way. I just posted that in this week's module. Hopefully, that this week's module should be posted by now. I posted it just before class, but I had to copy it from another class, so I just wanted to make sure it got up there. I'll check that when I get offline, and of course, text me or email me if you don't see it pop up. But I'm pretty sure I'll remember to do that. So we covered the centripetal acceleration and did exactly one example, not a very hard one or anything like that. I also introduced you to the idea of air resistance, or what we call drag force. And in that case, I told you that the force due to air resistance is either proportional to the velocity or proportional to the square of the velocity. And I also mentioned that the constant of proportionality is somewhat related to the viscosity of the fluid. It's also related to the cross-sectional area of the object that's falling, that sort of thing. But now I need to go back and work a little more robust problem on friction. Specifically, I'm going to work example 5, 7. And then after I finish example 5, 7, I'm going to go through and do a couple more centripetal acceleration problems. And then hopefully end up with air drag, or the drag force problem. So you can see how basically we define the, darn it, terminal velocity, as well as see how the equations are worked. It's actually just a solution of a differential equation that's pretty straightforward. So hopefully we can show you that. Again, just one more time, since a couple more people have logged in since I started that. Anybody have any questions before we get started? I'm going to go ahead and share my screen. Okay, so let me read you example 5, 7. Again, it doesn't appear that anyone had a question for me, so I'm just moving along. Let me open up the chat window too in case anybody has any question. I have gum in my mouth right now, so hopefully that doesn't become such a distraction that I choke on it or something. But anyways, if you see something fall out, it's gum. I'm not not throwing up or spitting or anything. But anyways, I want to throw it out, but I don't really have anything to throw it out with, and I thought it might look kind of disgusting to you guys, so I chose not to. Example 5, 7 says a ramp, a pulley, and two boxes. A box of mass m sub a equals 10.0 kilograms rests on a surface inclined at theta equal. I'm going to actually change this. It's not theta equal 37 degrees. I know what they're doing here. When I see an angle of 37 degrees, just like when I see an angle of 53 degrees, I immediately know, oh, they're trying to make use of the 3, 4, 5 triangle. So with my predisposition of enjoying at least three sig figs on everything, I went ahead and defined the angle as 36.87 degrees, actually to four sig figs, which is what the angle would be for the 3, 4, 5 triangle to four sig figs. So it says a box of mass m sub a equals 10.0 kilograms rests on a surface inclined at theta equal 36.87 degrees to the horizontal. It is connected by a lightweight cord which passes over a massless and frictionless pulley to a second box of mass MB which hangs freely as shown in figure 5.9a. If the coefficient of static friction is mu sub s equals 0.400, again, I added extra digits, determine what range of values for mass MB will keep the system at rest. B, if the coefficient of friction is mu k equals 0.300 and m sub b is equal to 10.0 kilograms, determine the acceleration of the system. So that's the problem we're solving. I've already drawn a diagram of the actual image of the actual system. So we have an inclined plane of angle theta. We have a mass m sub a on the incline. That's the one that's 10 kilograms. The m sub b, which is hanging freely, that's the one we have to determine in part A what mass range it will have to keep the object from accelerating. So we're going to work out that, and I'll explain how that goes. And then in part B, we're going to assume that MB is actually 10 kilograms, which you might suspect is outside of that range of values that is okay to keep it from accelerating. And in that, we're asked to find out what the acceleration will be. So in in this case, I'm going to imagine, for instance, that the box is going up the incline, and for that reason, I'm just going to choose the positive x direction to go up the incline. And as I told you before, when we're working with inclined planes, other than an example you'll see in this problem, which is when we're working with inclined planes to bank a curve, for instance. Other than that particular one example, we almost always want to go ahead and set our coordinate systems tilted along the perpendicular or along the tilted axis or tilted incline. So that's what I'm doing here. And in fact, I'm showing it two different ways because really what's going on here is MB, if it's too big, it's going to cause MA to go up the incline. And of course, if MB is too small, then MA is going to slide down the incline. So I did a free body diagram, or I'm planning on doing a free body diagram for MA for both cases. So the left one's going to be one case, the right one's going to be another, and then I'll have a separate free body diagram for the hanging mass M sub B. So let me start off by drawing all that. It is going to give me a chance to go back over some of the stuff that I taught you about dealing with inclined planes. So if you didn't get that from the previous videos, maybe it's another chance now. I'm going to go ahead and draw the object of mass M sub A right here. So that mass is 10.0 kilograms. Now I have a force acting on it. Remember the way we actually, or the way I'm trying to tell you guys to learn how to do a free body diagram is you first off take the thing that you're making the free body diagram and consider all the objects that's touching it. So right now, all we see that's touching M sub A is the inclined plane and the pulley. Okay, so the inclined plane and the pulley are both providing forces. One of those forces is in the positive y-hat direction, and that, of course, is the normal force. So that's F normal right there. We also have the tension in the rope, and that is going to point in the positive x direction, or positive x prime direction. And I call that just plain T. Your book calls it F sub T because it likes to only use F's with subscripts to represent forces. And that's fine. That's a fine philosophy. I just tend to use less subscripts and just always use a symbol. So what we have here is the two things that are touching it. Now the inclined plane's touching it another way as well. The inclined plane is also providing friction, so I've got to account for that friction. And if you're thinking about the diagram on the left, that's when the actual incline, or when the actual M sub A is being pulled up the incline. And if M sub A is going up the incline, then the friction force acts down the incline, and that would mean that the friction force is in the negative x direction, and that's a static friction, so I subscripted it S. Okay. Now, that's all the things that are physically touching M sub A. Then, once you're done with all the things that are physically touching M sub A, then you have to look for all the possible action at a distance forces, and that's pretty much the only one you've learned is gravity. So there is action at a distance on M sub A. The weight of the object, as dictated by gravity, of course, is W equals mg, and of course m is 10 kilograms, so m times g is 98.0 newtons. Notice I'm carrying an extra digit beyond the sig figs. Now, I drew that vector blue because it doesn't correlate, or it's not parallel to either the x-axis or the y-axis, so I have to break it down into components. What we did learn was that if this incline is the angle theta, then the x-axis would also be tilted at the angle theta. That's the whole purpose of us tilting it. So this angle right here is theta. And if you look closely, that means that there exists a right triangle right here, and this is the right angle. That being the right angle means that it's pointing to the hypotenuse. So that's our hypotenuse. And these two angles are these two sides, the vertical one and the horizontal one, are at 90 degrees with respect to each other. Because of that, you know that this angle is complementary to this angle because the sum of the angles in any triangle is 180 degrees. So we've already accounted for one of the 90s. So now we're left with a 90 of these two. Well, this one's 36.87. So that one's going to be 90 minus 36.87, which is 90 minus 36.87 is 53.13. So I'm just going to write it like this. I'm going to say this angle is 90 degrees minus theta, well, I won't even write the 53.13. We don't really necessarily need that. The main thing is we know it's 53.13. And then the other part of this that we have to realize is that even though it's not necessarily accurately drawn, this axis and this axis are supposed to make a 90-degree angle with respect to each other. So that means this angle, the 53.13, plus this angle gives you 90 as well. So these two angles are complementary as well. So if this is 53.13, then this one's going to be 36.87, and that means this angle right here is also theta, the 36.87. So now that we have that, now we can form a right triangle that has one leg parallel to the y-axis and the other leg parallel to the x prime axis. I should be saying primes each time. I keep forgetting that, but just fill that in. Okay. So the y component is obviously in the negative y direction, or negative y prime direction. And then the x component is also in the negative y prime, or the negative x prime direction. So I drew both of those red. And in fact, you should be able to tell that this will be mg sine 36.87 degrees. That's what the side is supposed to be. And of course, that quantity is equal to 98 times the sine of 36.87. And that gives you 58.80 newtons. And of course, I'm carrying again one extra digit. This one up here, the y component, is going to be mg cosine 36.87 degrees, which equals 98 times cosine 36.87 gives me 78.40 newtons. And again, I'm carrying one extra digit because we only had 3 sig figs with the mg, even though I gave you 4 sig figs with the theta. So now I've got all the components working up there. Of course, I also need some fundamental information, so I'll write solution. And that allows us to say the summation of the forces is equal to mass times acceleration. And it also allows us to say that the static friction force is less than or equal to mu static times F normal. And it also allows us to say that the kinetic friction force is equal to mu kinetic times the normal force. So that should be all the real equations we need. And this diagram that I just finished is basically when MB is, well, let's say it another way. I'm going to say when M sub A goes goes up the incline. Okay, so that's what this diagram is about, is when MA goes up the incline. Now I can sort of draw more or less the same diagram with one slight change over here, and this is for the case when MA slides down the incline. So there's our normal force. We still have the mass here that's 10.0 kilograms. We still have the vertical force that's 98.00 newtons. We still have this force Oops. Keep bumping into my iPad when I'm trying to draw a straight arrow, and when it does that, it makes the lines look like I'm drinking or got, I don't know. So, anyways, here's the forces. This one again is still going to be 78.40 newtons, and this one's still going to be 58.80 newtons, just like that. And in addition to that, we're still going to have the tension pulling up the incline. But this time, because the mass may actually be sliding down the incline, we're going to have the friction force up the incline. So in this case, the friction force is actually a positive, and that's F static points up. And that's basically it. That's the free body diagram for the MA in the two different scenarios. Now, this one is when M sub A goes down. So these are two scenarios here, and that allows us to write Newton's second law for both of those. Now, in addition to that, I'm going to have a free body diagram for the hanging mass. So part of the trick when you're doing this is in order to minimize the number of equations you have, you want to try to make the positive direction for the mass on the incline correlate with the positive direction for the mass that's hanging, so that when the mass on the incline goes a particular direction and you call that direction positive, you should make sure that the hanging mass goes that same direction and is positive. That way you won't have a weird equation like the acceleration of mass mb is equal to the negative of the acceleration of mass ma or something. So that's what we're going to do here. So we're treating the mass going up the incline as if that's the positive x prime direction. And when MA goes up the incline, MB will go down. So we're going to choose x prime to point down for the free body diagram of the hanging mass. So that's done like this. This time it's just M sub B. And the forces acting are, of course, uh, in the positive x prime direction is the force of gravity, and that's going to be mb times g. And then in the negative direction is the tension. And again, notice how the tension on the two diagrams to the right both point up the incline, whereas this one points in sort of in the opposite direction. And that's sort of what I was telling you earlier, is right now you just need to remember that that's the way it's got to be. Hopefully you can think it through on your own and sort of make some sense of why that's the case. But bare minimum, the best case scenario, or the worst case scenario, I should say, is that you're going to have enough experience with this that you're just convinced that, yeah, it does work. Maybe you haven't thought enough about why, but it does work. Okay. So, with that in mind, let me write the summation of forces in the y direction. Now, by the way, the summation of forces in the y prime direction is the same for both of these top right diagrams. So, I'm going to just draw that once and I'll sort of put it in the middle. Let's say the summation of the forces in the y prime direction equals mass sub A times A sub y prime. Now, in this case, like always, we're going to have a mass that's either sliding up the incline or it's sliding down the incline. But either way, the y prime coordinate is not going to change. So you could take one little interval and y prime final minus y prime initial is 0 minus 0. And then you divide that by the amount of time that elapses between it, and you get 0, because 0 divided by anything other than 0 is 0. And then you might say, okay, well, sometime later I have a different y final minus y initial, but both of those are still 0. So you again get the new velocity 0. Since you have a final velocity and an initial velocity both equal to 0, you have an acceleration equal to 0. So that's why we're going to say a sub y is equal to 0. Now with that, we can go ahead and write the forces in the y prime direction, and they are the normal force, which points upwards, so I'll write that as a positive, minus the mg cosine 36.87, which is 78.40 newtons, And that really is the only force acting because the rope or the string or whatever is actually designed or set up in this diagram to be exactly parallel to the incline. So it doesn't lift up nor push down on the box. So we set all that equal to 0, and that gives us that. Actually, I'll write it down here. That gives us that the normal force is equal to 78.40 newtons, and I'm just going to call this asterisk. Okay, we're going to put an asterisk by it just because that's something that I'm going to use, and I don't want to put a number on it because I'm using the numbers for the equations. Now, with that in mind, I can go ahead and examine, let's say we examine the rightmost diagram. We're going to say the summation of the forces in the x prime direction equals mass sub a times a sub x prime. In other words, mass times acceleration in the x prime direction. So that's what our Newton's second law, also called our equation of motion, if you will. So that's what Newton's second law gives us, and we're going to use that now to set up an equation, and then we can hopefully make some sense of it in such a way that we can figure out what minimum mass MB must have, uh, or excuse me, what maximum mass MB can have before it actually allows it to sit still, and then what smallest mass it'll have before it starts to cause it to go up the incline. So let's start off with this one. Since this one's the MA going down, we'll just remember that, and I'll tell you how we're going to address it. So the summation of forces in the x direction, you can see I've got a tension in the positive x direction. I've got a friction force in the positive x direction, and I have a negative 58.80 in the negative x direction. So that's going to be T plus F static minus 58.80 newtons is equal to 10.0 kilograms times A, because that's the only acceleration we're going to be dealing with, so I don't need to subscript that either. So let's call this equation 1. And now what I'm going to do with that is I'm going to try to imagine the scenario in which the acceleration is 0. In other words, if the acceleration is 0, that means all these forces are acting in such a way that they all just barely cancel each other out. So if a butterfly flies by for a split second, the breeze from the butterfly's wings will actually cause the actual mass to start sliding down the incline. Okay, that's the scenario. So if I set the acceleration equal to 0, that would be that bare minimum. Now I need that to happen when we're actually at a maximum of strength of the static friction force. So instead of just calling it F sub S, and the static friction force has to be less than or equal to mu sub S times F sub N, because of that, I'm going to go ahead and let it equal mu sub s times f sub n, because in that case, it's the largest it can be. And I'll just solve for the tension. So I'm going to go ahead and say, let A equal 0 and f sub s equal f sub s max, which equals mu sub s times f normal. So I should calculate here mu sub s times f normal is equal to, mu sub s is 0.4. So I'll say zero point 0.4 times 78.40, and that gives me 31.36. So this is 31.36 newtons, and that is the largest friction force that we can actually have here. I'm sorry, that decimal got kind of obscured. So I'll do it like that. So now we have the 31.36 newtons. We know what's going to be there. I'm going to let the A equal 0, and I'm going to solve for T. So writing all this down, I now have T plus 31.36 newtons minus 58.80 newtons is equal to 0, because I let the acceleration equal to 0. And now I'm going to solve for T. That means T is equal to 58.80 newtons minus 31.36 newtons, which equals 58.80 minus 31.36 gives me 27.44 newtons. But remember, over here, if the acceleration is really zero going up the incline, then the acceleration for the hanging mass is also zero, and you end up getting from, let me write Newton's second law real quick here, the summation of the forces in the x prime direction equals mass times acceleration in the x prime direction. Of course, this time it's mb. So in this case, I have mb G minus T is equal to M sub B times A. Now, if you allow A to equal 0, let's say, let A equal 0 and solve for T. In that case, I get T is equal to MB times G, and therefore I'm going to now realize that this 27.44, if I set that equal to MB times G, then I can solve for MB, and that'll give me the critical mass at which MB becomes just big enough, uh, or excuse me, just small enough to allow the M sub A to go down the incline. So now I'm going to say M sub B times G is equal to tension, which equals 27.44 newtons. And that means that M sub B is equal to, so I take the 27.44 and I divide it by 9.80, and that gives me 2.800 kilograms. So this is one of the key values. In other words, that's the value of mass M sub B, at which if it gets any larger than that, then the mass on the incline is going to sit perfectly still. Up to some limit, because there's going to be some mass where M sub B gets so large, then it's going to make it slide up the incline instead of slide down the incline. But if you put a mass smaller than 2.8, then it's actually going to make the mass M sub A on the incline slide down the incline. So we've got that one. Now I can sort of do the same thing with the other setup. Uh, so let me see. I guess the best way to explain that is I sort of want to write it right in here, but I'm afraid it's going to get too crowded. So let me start with writing the summation of forces and see how well it fits. And I'll write it in a different color just to see if that helps. So the summation forces in the x prime direction equals mass sub A times A in the x prime direction. In this case, we've got the T is the only force in the positive direction, and the friction force and the 58.80, which is the component of weight parallel to the incline, they're going to be negative. So in that case, I get T minus the friction force and then minus the 58.80 newtons is equal to M sub A times A. So that's another equation we can make use of. And in fact, I'll call that equation 2 just in case I need to refer to it. But I'm going to do the same thing with this one. I'm going to let A equal 0 and I'm going to let Fs be the largest value it could be. And then I'm going to realize that if the acceleration is really 0, then T is going to be equal to mbg. And I set those two equal to each other just like I did before. So I'm going to say, let's do it with green this time. Let A equal 0 and F sub S equals mu S times F normal. Now, when I do that, I end up getting the following. Solving for T, I get T is equal to, in this case, it's 58.80 newtons on the other side becomes positive, but notice the FS also becomes positive. So I'm going to take the 31.36, which is what F sub S is, maximum. So that'd be 31.36 newtons, like that. And now I can just say 58.80 plus 31.36 is equal to 90.16. So I'd say T, which equals MBG, is equal to 90.16 newtons. And that allows me to solve for M sub B by taking 90.16 and dividing it by 9.8. And in this case, I get 9.20 kilograms. So that's the other end. So now what we figured out is that if M sub B is 2.8 or smaller, it's not going to move. If M sub B is 9.20 or larger, it's also, or excuse me, it's not that it's not going to move. If M sub B is smaller than 2.80, then the M sub A is going to slide down the incline, and if M sub B is bigger than 9.8, then M sub A is going to slide up the incline. So the range at which it doesn't slide is from 2.8 to 9.2. So no sliding if 2.80 kilograms is less than or equal to M sub B is less than or equal to 9.20 kilograms. And this is our answer for part A. Anybody have any questions on that? All right. So this is sort of the nastiest of the nasty in terms of these Newton's second law problems because you really got to work out the scenarios. I will tell you that in the physics world, we kind of want you to come up with your own ways to do this sort of stuff. So there's a little bit more of a creative side that we expect of our physics majors. Whereas when I took statics, for instance, the calculus-based statics and the calculus-based dynamics, they gave us very specific techniques and methods we would use when we have multiple types of conditions. Like if you had this inclined plane, they'd have some step-by-step algorithmic process you could follow to find out exactly what is the smallest mass at which the object's going to accelerate up the incline and what's the biggest mass at which it's going to accelerate down the incline. And they'd have very specific algorithmic instructions to do that. And that's just because they want you to have clear and concise ways of thinking to apply physics as opposed to, invent new physics and discover new knowledge or whatever. Not to say that engineers don't do that. If all of them, and it doesn't have to be PhDs, but generally that's where it's done at the PhD level in physics or at the PhD level in engineering. They are discovering new science, they're discovering new knowledge, and that's sort of supposed to be the original purpose of the PhD is to generate new knowledge. That's also one of the fundamental ideas that many universities and people in the university systems have is that the purpose of a university is not to teach students. Again, that's not my philosophy. It's just a big philosophy within the academia. So at the university level, your job is to create new knowledge, not to necessarily teach students. If you get faculty members that can create new knowledge, but also happen to be good teachers, yay, that's great for them. But that's not their biggest concern. But as the world gets more democratic and stuff like that, we find that a lot more universities are actually requiring that. Even at, for instance, at Chapel Hill, which isn't one of the forefront universities in the nation, but it's still probably top 50 in the U.S. If you look there, for instance, when I was there, which was a long time ago, 1997-ish. Okay, when I was there, we actually had one faculty member that was sort of put on probation, saying we're not going to give you tenure until you get better at teaching. So they are getting better at in terms of thinking about students, but that's not necessarily the original goal. In fact, the Johns Hopkins University was created with the same model as the University of California system, and their idea was they were only going to have grad school and they weren't going to have any undergraduate students. But they've realized pretty quickly that they couldn't pay the bills without undergraduates. So instead of it becoming just a premier research university, it also had to start teaching as well. All right, now that I've got part A and I've also gotten off my soapbox, uh, we're going to work with part B. And part B is us saying, okay, now that we know that nothing happens between 9.8 or between 9.2 and 2.8 kilograms, we're going to take a mass of 10.0 kilograms, which obviously is going to result in MA going up the incline, and we want to calculate what the acceleration is. A big part of what you're supposed to learn here is that once you've exceeded the maximum force required, capable of or excuse me, the maximum force that the static friction is capable of generating, once you've exceeded that, it just automatically jumps to the kinetic friction. So we're going to go ahead and calculate the kinetic friction and throw that in. So I'm going to start off with the equation 2, which is the equation for M sub A going up the incline. And instead of using F sub S, I'm going to use F sub K. So I'll start with another color yet. So let's say B, using 2, we have T minus F sub K minus 58.80 newtons is equal to 10.0 kilogram. Actually, I should probably add an extra just because I'm carrying an extra sig fig, kilograms times A. I'm going to call this equation 2 prime because it's a slightly different version of equation 2. And now we're also going to have equation, and I never labeled this one before, but I will now. This equation right here is going to be called equation 3 because now I have to combine this equation with this equation to solve the problem. And not only that, I'm also going to say, using green over here now, I am going to calculate the kinetic friction. So F kinetic is equal to mu kinetic times the normal force. And mu kinetic is 0.300, so zero point 0.3 times the normal force, which was 78.40, gives me 23.52 newtons. So that's the kinetic friction. Now I can go ahead and add that and say that 2 prime is T minus 23.52 newtons minus 58.80 newtons. Wait a second here. Chi minus. Oh, yeah, that's right. Okay. I was just afraid I had accidentally copied the wrong equation, but now I see the friction force and the component of gravity parallel to the inclined plane are in the same direction, and that's what I expected it to be. And that's equal to 10.00 kilograms times A. Now I'm going to add 2 prime and actually I did not write that 2 prime very clearly. So I'm going to add equation 2 prime and equation 3. And the reason I'm doing that again is because you see in the equation 3, I've got a negative t, and the equation 2, I've got a positive t. So when I add those two, the t's are going to cancel out, and the MBG, which is now 10, is going to be as follows. So I'm going to go ahead and add these two. I'm going to get 10.00 kilograms times g, or excuse me, I might as well write it as times 9.80 meters per second minus t plus t minus now 23.52 plus 58.80 because they're both negative. Gave me 82.32, so I'm going to say minus 82.32 newtons is equal to 10.0. Notice the right-hand side of equation 3 is 10.0 kilograms times A, and the right-hand side of equation 2 prime is also 10 kilograms times A. So rather than write 10 kilograms here, I'm going to go ahead and write 20 because it's the sum of the two. So that'll be 20.00 kilograms times A. You can see that the T and the negative T cancel out. You can also see that the 10 times 9.8 becomes 98. So I'm going to do 98 minus 82.32. 98 minus 82.32 gives me 15.68. So I get 15. Oops, I wanted that to be in green. So this implies 15.68 newtons is equal to 20.00 kilograms times A, and A is what we're wanting to solve for. So A is equal to 15.68 newtons divided by 20.00 kilograms, and that gives me point 0.7840. 0.7840 meters per second is the acceleration, and that's the answer that we wanted for part B. Anybody have any questions on that one? I realize that's kind of a complicated problem, but hopefully you understood my explanation. You can watch it over and over again. In fact, I've explained it a bunch of different ways. If you look in this week's module, you'll see uh, uh, various problems that are like this one where you can see how I handled it. So feel free to check out those optional videos too. Any questions? I don't see anybody typing any or anything. All right, so now that we've done that, we've actually finished all the examples from chapter 5 regarding friction, and now I'm going to go back and handle some of the examples regarding circular motion. So remember, with circular motion, we had a few equations that we had come up with. The equations we came up with were A sub C, which equals the centripetal acceleration. And remember, centripetal means center seeking, so it points towards the center. And it's a centripetal acceleration. It's the acceleration required for an object to go into a circle to maintain a circular path. And that centripetal acceleration we found was omega squared times r, but we also found using v equals r times omega, we also found that it is v squared over r, where v is the constant velocity it has going in that circle, and r is the radius of that circular path. So that's the centripetal acceleration. In order to do that, we had to make use of the quantity omega, which is called the angular velocity, r, the angular frequency, and both of which are the same thing, but they're measured in radians per second. And it is given by 2 pi f, like that, which really just converts it from radians per second to, if you're solving for f, that would convert the f to cycles per second, because there's one cycle in 2 pi radians, or there's one revolution in 2 pi radians. So a revolution and a cycle sort of mean the same thing. And that, of course, tells us that f is just the frequency. Oops. And that is measured in cycles per second. are, somebody just came in as well, are revolutions per second, are what we call hertz, which is the same thing as cycles per second. And of course, you might actually see some old literature, especially in government documents, where they call it CPS, cycles per second. But that's what the frequency is. And then T is the period, period of rotation, R of revolution, R of oscillation. So notice there's three versions here: period of rotation, period of revolution, and period of oscillation. So if you, for instance, have an object that's rotating about an axis through itself, then that is called rotation. If you have an object that is orbiting around another object, then that's called revolving around that object. And the period would be the period of revolution, meaning the time required for it to go from here to here again. Just like the period of rotation was the time required for it to go from here to here again. And then finally, the period of oscillation. If you've ever had, for instance, one of those fans that's called an oscillating fan, it goes back and forth like a pendulum. In that case, if you think of it as a pendulum, you could say the period of oscillation is the time required to go from the peak on this side to the peak on the other side and back to the peak again. You could also consider it straight down to the max to the right, and then to the max to the left, and then straight down again. That's the amount of time that one period lasts. So that's what the period is. And with that, we can actually make the conclusion that the frequency is 1 over the period, or the period is 1 over the frequency. And that should show you the units of period are normally seconds. It's actually the dimensions are time. But you could use, of course, years and months and hours and days and that sort of stuff. But any of those would work. So that's some of the stuff we were able to explain last time. So I wanted to make sure you guys were up to speed on that. So that's some of the quantities we'll need to be using. Now we've already done example 5.8, so that allows me to jump into example 5.9. So let's look at example 5.9. Example 5.9 says moon centripetal acceleration. The moon's nearly circular orbit about the Earth has a radius of about 384,000 kilometers and a period T, excuse me, of 27.3 days. Determine the acceleration of the moon toward the Earth. So we were given that the radius of the orbit, which is what the r corresponds to in AC equals v squared over r, is equal to 384,000 kilometers. Now, remember, within your book, and therefore, if you ever get a multiple choice test question like this, within your book, 384,000 has an ambiguous number of sig figs. If I were in my system, if I were to put just a decimal place right there, just like that, then that would clear all that up and it would make it have 6 sig figs. But your author doesn't necessarily abide by that rule, and he's telling you explicitly if someone says 384,000 and you got those 3 zeros, you have no idea if those zeros are significant or not unless they specifically told you. So the answer for that type of question would be ambiguous, just in case you run into that on your practice test or anything. So we've got that, and in fact, kilometers is not useful for me, so I'm going to call this 3.84. Notice 3.84 times 10 to the fifth would be it in kilometers, but I want it in meters, so I'm going to say it's 3.84 times 10 to the eighth meters. So that's the radius. of the orbit. We also are told that the period t is equal to, and by the way, is this period of revolution or is this period of rotation? Anybody? Anyone? Anyone? Those of you who came in late, like some of you've been coming in as we've been speaking, you can just go ahead and chat me your first and last name too, so you won't forget till later. So, anyways, the period is 27.3 days. I'm going to have to deal with that. It is a period of revolution because this is the moon revolving around the sun, around the earth. So keep that in mind. And what they want us to find out is A sub C. So first off, I'm going to use solution A sub C is equal to V squared over R. And I'm going to point out something to you guys. Hopefully, you understand it. The derivation that I did last time, we discovered that by using that vector valued function, in other words, a vector field, if you will, by using that, we actually found a vector that basically rotated in time like this. So it was a vector that was pointing perfectly to the right horizontal at t equals 0 seconds. And then it moved counterclockwise in a complete circle until a time t, the period, was had elapsed. And in that scenario, what we discovered is that the velocity when such a motion is activated, is in action, the velocity is a constant. And that means if the velocity really is a constant, then the average velocity is the velocity. So that tells us that the velocity is actually equal to the distance traveled divided by the time taken. And again, I'm not considering weird things like the displacement versus the distance. I'm actually going to say the distance traveled because I really want in some sense, you could say I want the speed. But the big thing here is the moon is essentially following a circular orbit, and the distance around a circle is called the circumference. Therefore, the distance is equal to 2 pi times r. And then the time taken for it to complete that circle is the period of revolution, which would be t. So that's another equation we're going to use. And I've got to go ahead and convert my period, which is 27.3 days. And I've got to convert that to seconds. So we know that 1 day is equal to 24 hours. And we know that 1 hour is equal to 3,600 seconds. So we can say 27.3 times 24 times 3,600. And then, of course, we're dividing all that by 1, but that doesn't change the numerical values. But we have managed to cancel out the h's, and now we've got 2.359 times 10 to the 6th times 10 to the 6th seconds is the number of seconds in 27.3 days. So now I can go ahead and calculate what the V is, and then I can use the V to square it and put it over R. So I can now say V is equal to 2 times pi times 3.84 times 10 to the 8th meters. And then I'm going to divide that by the period, which is 2.359 times 10 to the 6th seconds. That gives me 2 times 3.14159 times 3.84 times 10 to the 6th. And now I'm going to divide all that by parenthesis 2.359 times 10 to the 6th, close parenthesis. I did find one calculator once, or at least I seem to have found a calculator once, that when I did division by a scientific notation number, it seemed like it divided by the mantissa, the part without the times 10, and then multiplied by the power of 10. So I now live in fear that it was this calculator, so that's why I did parentheses there. You don't necessarily have to do that, but if your calculator shows you do, then you better. So this gives me 1,000 or 1 point. Oh, it's 10.23 meters per second. That does not seem right. Let me see. Ah, I see why. Okay, I made a mistake on my calculation. It's 2 times 3.14159 times 3.84 times 10 to the eighth. Now I'm going to divide by parenthesis 2.359 times 10 to the sixth, close parenthesis. And now that's going to give me, that's more like it, 1,023 meters per second. So that's a rough estimate of how fast the moon is going, on the order of 1,023 meters per second around the Earth. And in fact, that's quite a bit slower, for instance, compared to, if I remember correctly, the last time I calculated the velocity of the Earth around the sun, I think it was larger than that. But that's also around 2.2 times that for miles per hour, so 2.24, for instance. So in miles per hour, that's around 2,300 miles per hour. That's just for your own intellectual edification. So on the order of 2,300 mph. We don't need that number. It's just I wanted you to know it in terms of numbers that you might be slightly more familiar with. Now I'm going to go ahead and calculate the acceleration, and the acceleration centripetal is v squared over r. So I'm going to say 1023 meters per second quantity squared divided by 3.84 times 10 to the eighth meters. You can see that the meters per second, when you square that, you're going to get meters squared per second squared, but then you're going to divide that by meters, so that's going to give you meters per second squared. So 1023 squared is a big number, and then we're going to divide it by parentheses 3.84. Ooh, 3.84 times 10 to the eighth, and that gives me 0.00272. Now, we've been using 3 sig figs on everything, so this should be good to 3 sig figs, and I get 2725 meters per second is the acceleration of the moon, and that's the answer. Anybody have any questions on that? All right. Looks like no one has any questions on that. And we'll find out later that that's actually a calculation that Newton did when he uh, conjured up his idea of what the law of gravity would be. And his first check was to calculate the acceleration of the center of the Earth, or excuse me, calculate the force on the moon as a result of the Earth, and find out from that what the actual acceleration was. And he got exactly the same number, and therefore he knew at that instant that he was the only person on planet Earth that knew exactly what caused the Earth to orbit the sun and what caused the moon to orbit the Earth, and so on and so forth. So it's a pretty neat discovery. Anybody have any questions on this? Now, your book goes in and talks about some of the applications. It talks about centrifugation, which is, what's used in the medical field when you, for instance, draw blood. You can then separate out the platelets by splitting in a centrifuge. But we also use centrifuges in physics, in the nuclear physics world. For instance, you're probably hearing things about Iran right now, and one of the things we do is, it turns out uranium, when we find it, is in the natural form of uranium 238, but uranium 235 is what we use for nuclear weapons and for nuclear facilities for generating power in nuclear power plants. And in fact, 99.3% of the uranium on planet Earth is in that 238 isotope. And what we can do is actually put the uranium in very specific, very specialized centrifuges, and that can actually increase the percentage of uranium by separating out the 235 from the 238, and that can give us a pretty large purity of uranium 235. In fact, for nuclear weapons, we need over 80%, and for power plants, we need somewhere between 3 and 20%. So another thing you can use is we use centrifuge type scenarios to train astronauts to deal with high G's of taking off and returning to orbit and stuff like that. So that's some of the applications. I'm going to skip example 510, which is ultra centrifuge. Not because it's not important, but it's because it's really, really simple. So that doesn't mean you shouldn't know it or anything. It's simple to do. So just make sure you do it. But I'm going to move on to the next section now. And we're talking about the dynamics of circular motion. So what we're talking about here is the dynamics of circular motion, and what they're telling us and showing us is that basically, if you take a string and tie a ball on the end, and you hold the other end of the string, you can spin it over your head like this, and it's going to go in this pattern, either counterclockwise or clockwise. And in order for that to maintain a circle, the tension in the string has to be big enough to supply the centripetal acceleration necessary for that rotation. If at any instant the string were to break, you might think that, let's say, the mass was right here to my right and it was coming, towards you guys in the camera, you'd think that if the string broke, you might believe that it would shoot straight out to the right. In fact, no, that's not at all what happens according to Newton's first law of motion. As it comes around here, when it reaches this point, its velocity, as I said, is pointing right towards the camera, and therefore, if the string breaks, it's going to continue to go straight forward that way. That's a big thing to understand. It's not going to shoot out to the right like it's a centrifugal force. Okay, there is no real centrifugal force. In fact, that's a made up force, if you will. Specifically, if you work out Newton's second law for a rotating reference frame, it turns out when you take the derivatives of something rotating, you have multiple terms due to the chain rule and stuff like that. One of those terms looks just like centrifugal acceleration, but it's actually centripetal acceleration. It's just on the left hand side, or excuse me, the right hand side where ma is. But if you pull it over to the left hand side where the summation of forces is, then it changes sign, and because it changes sign, it changes from a centripetal acceleration to a centrifugal, and since it's on the left side now, it's a force instead of an actual acceleration. So that's why it's not really a real force, centrifugal force. Okay, let's look at example 511. Example 511 says estimate force on a revolving ball horizontal. Estimate the force a person must exert on a string attached to a 0.150 kilogram ball to make the ball revolve in a horizontal circle of radius 0.600 meters. The ball makes 2.00 revolutions per second, as in example 5.8. Ignore the string's mass. So what we're talking about here is a ball following in a circular path like I have drawn here. And I'm trying to make it look as realistic but good as possible. Now, the string, for instance, would be right here to the center. And in reality, when you're spinning like that, you'll see that the string is not exactly horizontal. It's tilted down a little bit. But if you spin it fast enough, then that angle can get pretty small. So we're gonna, on as a first order approximation, we're gonna go on the assumption that it actually is a very, very, very small angle. So we'll even ignore it. I have to write down that the mass they gave us was 0.150 kilograms. The frequency they gave us was 2.00 revolutions per second, which also means that the period, which is 1 over the frequency, is 1 half, which equals 0.500 seconds. So it's either the frequency is 2.00 hertz or the period is 0.500 seconds. And again, what we want to know is estimate the force F equals question mark. So what we're looking at here is the ball of mass M, and the force that has to work here has to point towards the center. So I'm going to say I'm going to say that that is a positive direction. I'm going to use Newton's second law radially. So I'm going to say solution summation forces in the radial direction equals mass times acceleration in the radial direction, and A sub c is equal to v squared over r. But I'm also going to use the fact that v is equal to 2 pi r over the period. So that'll help us as well. They did tell us also that the radius of the circle r is equal to 0.600 meters. And in reality, what's going to happen is the string is actually going to tilt downward by some angle phi, and then the ball is going to be here. But we're going to sort of ignore that right now. Okay? So the summation of the forces in the radial direction equals mass times acceleration in the radial direction is going to give us the following. I'm going to draw a coordinate system where this is, let's call it the radial direction. In other words, I'm pretending like it's like an x-axis, but it's an x-axis that happens to be moving uh, at each specific instant. But what we're looking at is a snapshot of it at that point in time, and it points in the x direction, but it's technically at that point in time, it's in the radial direction. So the mass is here. We actually have, in principle, because you could draw a y-axis here, then you could have a weight mg acting downward, and then you would have a string force, which is not exactly horizontal, so we have to draw it blue or some color other than red and green. And what you would see is that that could be made up of a green force upward and a green force horizontally, and that this angle right here is phi. That's really what's happening here, but we're going on the assumption that phi is darn close to zero. So what we're going to do for our free body diagram is we're going to say the only force acting is the tension in the rope, which is chi, and I'm going to ignore that itty bitty component in the vertical direction, that itty bitty component by saying the sign or by saying phi is close to zero, that means the sine of phi is really close to zero as well, and therefore that means that vertical component, which could be gotten by taking the sine of phi, and then multiplying it by the hypotenuse, for instance, that would actually be close to zero as well. So with that in mind, that allows us to skip the mg completely, and our equation of motion, Newton's second law, becomes T is equal to mv squared over r. Because the A on the right-hand side of Newton's second law is the centripetal acceleration that's necessary, or else the object's not going to go in a circle. So this is just a quick and dirty estimate of it. Now that we have that, we can go ahead and calculate exactly what that is. But in order to do so, I still need the velocity. So we learned earlier that the velocity was 2 pi r over t. So that's going to be 2 times pi times 0.600 meters. And all of that is going to be divided by 0.500 seconds. So when I do 2 times 3.14159 times zero point 0.6, and then I divide that by 0.5, which is the same thing as multiplying by 2, I get 7.540, which is one extra sig fig, or one extra digit beyond the sig figs. So that's 7.540 meters per second. Therefore, we get the tension is equal to 0.150 kilograms times 7.540 meters per second squared over 0.600 meters. So with that in mind, I'm going to say 0.150. This is m times v squared over r. That's what's going on here. So 0.150 is the m times the answer I just got squared. And then I'm going to divide that by zero point 0.6. And that's going to give me 14.21. And that is 14.21 newtons because kilograms times meter squared per second squared would be a newton times a meter, but then I'm dividing by a meter, so that'd be a newton. So I've got that is equal to the tension in the string, and that's the force that we actually have to apply to it to make sure it stays in a circle. So about 14.21. We only had 3 sig figs, so technically I have to underscore that 1 because that's not a sig fig, and I really meant to do that in purple, and twice I wrote it and still didn't get it in purple. Anybody have any questions on that one? Now, if we tried to do it without making that quick approximation, let me show you exactly how that would be done. So I'm just going to call this extra. So the free body diagram for this would really be more along the lines of a mass like that, an axis like that, an axis like that, and our force downward would be m times g. And I'm just going to work this with symbols as opposed to plugging in the numbers because that takes more time to calculate. I'm also going to have this tension T acting up at an angle phi. Now that tension T is going to be broken into components. One component, of course, is green and points in the positive x/radial line direction. So let me call that radial again. And then the other component is going to be this one right here. So what we can see is that the y component is going to be t sine phi, and the x component is going to be t cosine phi. Now we can take the summation of the forces in the y direction equals mass times acceleration in the y direction. And in this scenario, we're just imagining that the string is constantly going to be tilted at that angle phi so that the mass goes around in such a way and never changes its y coordinate. So just like the y coordinate when we were trying to determine the normal force, the y coordinate didn't change there. So we said the acceleration in the y direction was 0. We're going to do the same thing here. We're going to say the acceleration in the y direction is equal to 0. So in this case, we're going to get t sine phi is equal, or excuse me, t sine phi minus mg is equal to 0. And that tells us, for instance, that, well, that could tell us, for instance, that t sine phi, this is just like the fuzzy dice problem we did earlier, so t sine phi is equal to mg. I'm going to call that equation 1. Now I'm going to take the summation of forces in the radial direction equals mass times acceleration in the radial direction. And we got to realize that in order for this to be happening, the acceleration has to be this way, and it's a sub c is equal to v squared over r. So I can now plug this in, and we see that we only have t cosine theta as the only force acting in the horizontal direction. So that gives me t cosine theta, or excuse me, it's cosine phi. I don't know why I changed it to theta there. Cosine phi is equal to mv squared over r, and that's going to be equation 2. So the smart thing to do here is to divide equation 1 by equation 2. So I'll say divide 1 by 2. Now, again, there's always a danger dividing an equation by another equation, but notice here, in order for either equation to be 0, specifically in this case 2, you would have to consider the angle being 0 and the angle being, or actually you'd have to consider the angle being 90 degrees to get 0 of cosine. So that's just not a physical problem that we're interested in, so it's not a big deal. So with that in mind, I get t sine phi over t cosine phi is equal to mg over mv squared over r. You can see that the m's canceling out. You can also see that the t's canceling out, and you can see that the sine of phi divided by the cosine of phi is actually equal to the tangent of phi. So with that in mind, we could go ahead and use this, for instance, to solve for phi. We would say phi equals the tangent inverse of GR over v squared, and you'll find out that this is a form of equation that you can use over and over again, but that's basically it. So now we have the phi. We could go back now and calculate with that angle phi exactly what the tension would have to be, and so on and so forth, and we would get a slightly different answer than the 14.21. If you want to do that for an extra credit and go back and figure out what the tension is, as well as the angle phi, then you can do that for an extra credit. But hopefully that helped you better understand what your author's talking about in the note. He said, or actually in the note, he says to include the effect of mg, resolve ft into components and set the horizontal components of ft equal to mv squared over r and its vertical component equal to mg. So that was me just sort of carrying out that. Anyone have any questions on this? Okay, I just realized it's 6 minutes over. I completely went over time, so uh, you guys are free to go. I apologize for that. Have a good one. I'll wait till the last person to leave in case you have any questions. But that's essentially it. The only thing I haven't done is a couple more examples of this type of motion. I might do some videos and just share them with you later. But we're going to move on to chapter 6 next. So I'm probably not going to spend more time in class for it, but I might make some more videos for you. Of course, I've given you a ton of videos so you can watch the other ones, but we are done with this. So have a good one, everybody. Thanks for coming. And as I said, let me know if you have any questions, and I'm going to wait here till the last person leaves.
I think we go to 740
Oh,
typically.
Jesus. I just saw that. Thank you. Thank you. I completely forgot that. I was wondering how the time got away from me. Yeah, I just looked up and I didn't even see the six. I thought it was 7:46. Whew, thank you. That makes it feel a lot better because I didn't want to do that with the other examples. So thank you for correcting me on that. Of course, if y'all want to leave, you're always welcome to leave. So I apologize for getting y'all excited about nothing. Now let's go ahead and do. This is a really good example. Example 512: revolving ball in a vertical circle. So let's work on that one now. Anybody have any questions about that last one before I go on, though? We'll file that under poor instructors going see now. All right, here we go. Example 512. So it says a revolving ball, vertical circle, a 0.150 kilogram ball on the end of a 1.10 meter long cord of negligible mass is swung in a vertical circle. A, determine the minimum speed the ball must have at the top of its arc so the ball continues moving in a circle. And then B, calculate the tension in the cord at the bottom of the arc, assuming the ball is moving at twice the speed of part A. So we've got a mass that equals 0.150 kilograms. We have a string whose radius when we spin it is going to be 1.10 meters, and it's a vertical circle. Okay, so I'll draw that in a second and help you make some sense of it. And for part A, we're wanting to determine the speed of the ball must have at the top of its arc so that the ball continues to move in a circle. So V min at top is the question mark, and then part B, if V equals 2 V min at bottom, uh, what is the tension? Okay, so that's the question. Now I'm going to go ahead and draw a circle, and I'm going to use my note-taking program to make a really good circle, as you saw I just did. I'm going to say the center of the circle is roughly here at this spot. And what we're going to imagine is that we have a ball right here of mass m, and it's moving with a velocity v. And what we want is to draw a free body diagram of that. So I'm going to draw a free body diagram for the ball at the top. And what we get is this. At the top, we're going to have let's say the downward direction is the positive y direction, and let's say the left direction is the positive x direction. And with that in mind, what we see is that the weight is acting in the positive direction, so that is mg. But we also have that the tension in the string is pointing in the positive direction, so that's also t. And we know that the acceleration has to be AC. So the acceleration has to be that particular direction. So now we can go ahead and write out the summation of the forces in the y direction equals mass times acceleration in the y direction. And for this case, we see that the forces are T plus mg is equal to mv squared over r. Okay. Now, if you want to find the minimum speed, what you need is that acceleration be completely supplied by the mg, and therefore we're going to consider allowing the t go to zero. If we imagine t approaching zero, then v approaches, oops, then t approaches, or v approaches v min. In other words, you've probably done this before if you ever been on the beach and you take a bucket of sand or water or whatever. If you spin it just right, you can spin the bucket and the water or the sand won't pull out even though it's upside down. Well, you can keep going slower and slower and slower. And at some point, you'll get going so slow that the water will just dump on your head to some extent. What we want to do is just figure out the bare minimum of that. Well, the bare minimum of that is when the gravity is just exactly enough, the m times g is just exactly enough to supply the centripetal acceleration, and then the water will stay in the bucket because that force that's pulling it down is the active force that's pulling it down to allow it to continue going in a circle. So with that in mind, we end up getting mv squared is equal to mv, or is equal to mg. So we get mg equals mv squared over r, which clearly shows that the m's cancel out. So this should actually give us, and I should write the min on that too. So I'll say v min. So therefore, v min is going to be actually equal to the square root of g times r. So that's the actual V min. We can go ahead and plug that in. V min is equal to the square root of 9.80 meters per second times the r, which is 1.10 meters. Notice meters times meters per second gives you meters squared per second squared. And when you take the square root of that, you get meters per second. So I'm going to say 9.8 times 1.1 gives me 10.78. Now I'm going to take the square root of that, raise it to the zero point 0.5 power, and that gives me 3.283 meters per second. So V min is equal to 3.283 meters per second, and that's our answer to part A. Everybody follow that? Anybody have any questions on that particular part? Okay, so now for part B, they say what's going to happen when you get to the bottom if the thing is actually traveling at twice v min. So I'm going to draw the mass again, but this time at the bottom, and then I'm going to draw another free body diagram. And this time we're going to say the v is equal to 2v min. And of course, that means about 6.567 meters per second with one extra digit again. So now we want to do that. Let's draw another free body diagram. Okay, so in this case, we have the mass right there. I'm going to consider upward to be the positive y direction, and I'll consider to the right to be the positive x direction. And with this in mind, what we see is we're going to have a tension in the string that acts upward, which is the positive direction. Almost wrote mg there. That's T. Now, in addition to that, we don't get a hiatus from gravity, so we're actually going to have a mg acting downward. And of course, the acceleration here has to be a sub c. So that's the acceleration of the mass at that particular point. So now we can write the summation of the forces in the y direction equals mass times acceleration in the y direction. In this case, we're going to get T minus mg is equal to mv squared over r. I want to make sure. Yeah, I did. I just double checked there. My AC was in the same direction as T and mg. That's why it was positive. If I had AC pointing up in that top diagram to the right, then I would have had to call that negative v squared over r. But in this case, the AC is pointing in the B diagram, AC is pointing up, and that's the positive direction anyway, so it'll be positive here as well. But that's something you've got to think about. Once you decide, what direction is positive, then you got to make your forces in those directions, but you also got to make your accelerations in those directions as well. So you either have to expect that solving for acceleration gives you a negative if it's pointing in the negative direction, or you got to force the acceleration to be negative to solve the equation properly. So in this case, everything was positive, so it wasn't a big deal either way. But in this case, we got to go ahead and add in the new velocity. And from this, we can get that the tension is equal to m times g plus v squared over r. Now I can start putting in the numbers. The mass is 0.150 kilograms. G is 9.80 meters per second. And V squared over R is going to be 6.567 meters per second squared over 1.10 meters. And I have a square bracket over here as well that you can barely see, but that's okay. Now I'm going to take 6.567 and I'm going to square that, and then I'm going to divide it by 1.1, and that's going to give me 0.150 kilograms times 9.80 meters per second plus 39.20 meters per second. So 39.2 plus 9.8 gives me 49.0 meters per second. And now if I multiply that by 0.150, I get that the tension will actually be 7.351 newtons, which equals the tension. And I can circle this, and that's the answer to part B. Anybody have any questions on that? All right, so that's how you do this type of centripetal motion problem. You can see, for instance, you could go ahead and calculate what the tension would be if it was going this fast that it reached the top, all sorts of stuff like that. You could also see that the tension in the string could be perpendicular if you were trying to consider, for instance, what happens when the mass is over here on the right hand side and the velocity is that way. That's a whole different scenario. But that's some of the types of things that you can actually add to these problems to make them a little bit more complicated. But you'll see plenty of examples when you start taking your practice test or when you do your homeworks as well. So, anybody have any questions on any of that before we move on? All right. Looks like we're doing pretty well here. So let's consider, yeah, it looks like we still got 40 minutes. Yeah, 40 minutes. And I'm looking at example 513. Example 513, a small ball of mass M suspended by a cord of length L revolves in a horizontal circle of radius R equals L sine theta, where theta is the angle the string makes with the vertical. In what direction is the acceleration of the ball, and what causes this acceleration? Calculate the speed and period, time required for one revolution of the ball in terms of L, theta, G, and M. So that's the problem we're trying to solve. Let me draw a diagram real quick to make some sense of this. So here's our ceiling, like that. Okay. And let's say right here is vertical. And what we have over here is a string of length L at an angle theta. And then at the bottom of that is a mass M. And in fact, what's happening is this pendulum is going around in a circle like this. That's what makes it a conical pendulum. If it was just going back and back and forth, left and right in a plane, then it would just be a regular pendulum. But in this case, it's actually going around in a circle. Okay. So we've got that. The L is actually the length of the string. Now we can draw a free body diagram. We do know that the theta we're supposed to know, the L we're supposed to know, we're supposed to know gravitational acceleration, and we're supposed to know M. So L, theta, G, and M are known. Now, when you're solving physics problems, if you're working them algebraic like this, that's really a nice thing because when you solve them, you've solved an infinity of problems. You've solved it for all the possible values and combinations of values of L, theta, G, and M. So, by all means, keep thinking of that, and it's the sort of the holy grail of theoretical physics is can you solve these problems like this symbolically so that you just have a formula that you're going to apply at every problem like it. With that in mind, let's go ahead and show you how to solve it. Your book is going to say that we want to put the x-axis to the right and the y-axis up. I've told you about that. You can also do this little thing and just say like that. That works as well. But I want to go ahead and draw a free body diagram separate from the picture here. So my free body diagram has the x-axis pointing that way. It has the y-axis pointing this way. It has the mass m right here. Of course, that means there's going to be a force of gravity acting downward, which is mg. There's going to be a tension force, which is not parallel to the x or y axes, so I'm just going to use green for that. And it's going to be in this direction, t, and that, of course, means that angle is theta, but that also means this angle is theta. There's a rule in geometry, in case you haven't covered this before, but what I tell my students is imagine a railroad track. So here's one railroad railing, and here's the other railroad railing. Those are the railroad tracks. And if they're parallel, then you can take a piece of rebar and lay it across the railroad tracks. And when you do that, all the angles in here, this angle, this angle, this angle, and this angle, are all called interior angles because they're between the railroad tracks. This angle, and this angle, and this angle, and this angle are all called exterior angles. And there's some rules that specifically in a geometry class, they would tell you if you see an arrow like this and another arrow like this, that's code for saying, hey, these two lines are parallel. But if you don't see them, then you cannot assume the lines are parallel. I said they're railroad tracks, so that makes them automatically parallel. So, with that being parallel, there's a neat rule that happens. For for parallel lines crossed, let's just say for parallel lines. So for parallel lines, alternate interior angles are equal. That's one result. Another result is corresponding angles are equal. So that's how I was able to make that conclusion that the angle theta that I drew to the right was the same as the angle theta that I drew to the left. I was picturing the dotted vertical line as one railroad track and the y-axis as the other railroad track, and the transverse line was the rebar across there. That was the actual tension. So let me show you what we mean by alternate interior angles. So alternate interior angles, for instance, would be this angle and this angle because they're both interior, but they're on alternate sides of the transverse line. So these two are equal, and we can indicate they're equal by putting a single slash mark. It turns out that these two are also equal to each other because they're also alternate interior angles because they're on the alternate sides of the transverse and they're interior. Now, in addition to that, we have this angle right here, which corresponds to this angle right here because they're corresponding angles. See, both of them agree that under them is a railroad track and to the left of them is a piece of rebar. So they both say to their left is rebar and to under them is a railroad track. So that makes them corresponding angles. So those two are corresponding. We could also say that this angle and this angle is also corresponding. And not only that, there's also something called vertical angles. So when you have a line like this angle is equal to this angle, and this angle is equal to this angle because these are vertical angles. Now, they're not vertical in the sense of vertical versus horizontal. They're vertical in the sense that they're on opposite sides of a vertex, specifically this dot. So that's some of the geometry you sort of need to be able to understand in this physics class. So hopefully, you only run into it once or twice. A week or something like that. So just keep it in mind. Whenever you have two parallel lines and they're crossed by a transverse line, alternate interior angles are equal, corresponding angles are equal, and then of course vertical angles are always equal. Period. It's not about the rays being parallel or not. It's just about vertical angles are always equal because of the way they're made. Now that we have all that, we can start trying to make sense of this free body diagram. In order to deal with the free body diagram, I've got to actually break the tension up into components parallel to the x and y axes. So I get a x component that is actually, oops, I get an x component that's positive, so I'm going to use a green vector. Oh, that was the reason I didn't want to use a green vector before, because green is my positive direction. So there's my tension force. Sorry about that. All right, so there's my tension force. That means this one is uh, T sine theta. And then also there is a positive y component as well. And this one is T cosine theta, like that. Okay. Now, what we have to have is, if this thing is really going in a circle like this, then the acceleration needs to be towards the center of the circle. And that means the acceleration is actually this way, and it's a sub c. Notice how I keep drawing the acceleration vector near the free body diagram, but not on the free body diagram. Our free body diagrams in physics are all just forces. You don't put accelerations on there because you inadvertently add an acceleration to a force, and that's not right because they're not the right units. But now that we have that, we can sort of make some sense out of it. So I'm going to take the summation of the forces in the y direction equals mass times acceleration in the y direction. Again, this pulley, or this conical pendulum, is supposed to be in some kind of equilibrium state so that the mass never changes its y coordinate. Because of that, again, we're going to assume that the acceleration in the y direction is equal to zero, and that gives us t cosine theta minus mg is equal to zero, which tells us that t cosine theta is equal to mg, and I'm going to call that equation 1. Now I'm going to take the summation forces in the x direction equals mass times acceleration in the x direction. And this time the acceleration has to be that centripetal acceleration, a sub x, which notice is in the direction of the positive x-axis. That's why I chose that direction. Oh, that because the book chose it. But anyways, the only force acting in that direction is t sine theta. So I'm going to say t sine theta is equal to mv squared over r. And r, of course, is something we got to figure out. Specifically, we know that L is this distance, and this distance right here, for instance, the height would be L cosine theta, and then this distance would be L sine theta. So r should equal L sine theta. So with that in mind, I can go ahead and write T sine theta is equal to mv squared over L sine theta, like that. And that gives me yet another equation. And in fact, we can take equation 1. So from 1, we find that the tension is equal to mg over cosine theta, which I'll call this 1 prime. And we can actually go back and plug that into the other equation if we so desire. And we can say 1 prime, and here's equation 2, gives us the following: mg over cosine theta times sine theta is equal to mv squared over L sine theta. Now, what we're supposed to find here is in which direction is the acceleration of the ball and what causes the acceleration. We can see the direction of the acceleration is clearly in the positive x direction, or specifically, it is horizontally from the ball towards the center of the circle, which is roughly right here. So that's the direction of the acceleration, like that. And what is causing it is the horizontal component of the tension. So there's our answers to part A. Part B says calculate the speed and the period of the ball. So now we can go about calculating the actual speed by solving for V. You can see already that the mass on the two sides is going to cancel out. And from this, we can get V. Oops, change colors. From this, we can get V is equal to G L sine squared theta divided by, that's G times L times sine squared theta, divided by cosine theta, and then we got to take the square root of that. So that is actually the velocity. So this is part B. We also know that the velocity is equal to 2 pi r over t. So that means that t is equal to 2 pi r over v, but we already figured out that r is L sine theta. So this is going to be t equals 2 pi times L sine theta over v. So that's going to be 2 pi L sine theta divided by the square root of GL sine squared theta over cosine theta. That is not necessarily very neat, but we can pull it all inside of the square root. I'll leave the 2 pi out in front because that's a typical formula that you'd have for the period of something, is 2 pi times something. So if I pull the L and the sine theta inside, that's going to become L squared sine squared theta. And then I already have, in the bottom was cosine theta in the bottom of the bottom. So when I divide by that fraction, that cosine is going to come up to the top, and that's going to be cosine theta up there. And then I have down here GL sine squared theta. So you can see now that one of the L's is going to cancel out. Both of the sine thetas are going to cancel out. And we're able to find that t should equal 2 pi times L cosine theta over g. So we can finally say that t is equal to L cosine theta over g. Oops, left off the 2 pi and the square root. Actually, I can do that better this way. Let's say t is equal to 2 pi square root L cosine theta over g. So that's the other answer for part B. As I said, part A was acceleration points to middle of circle and uh, supplied by t, or excuse me, by t times the sine of theta. So that's our answer to part B. I mean to part A, excuse me. Everybody all right? Okay. So that's our accelerate, or that's the explanation of part A, and that's part B. Anybody have any questions on that one? All right. So now we're going to get to highways, banked curves, and unbanked curves, that sort of thing. So, for instance, the first example is going to be skidding on a curve. A 1,000 kilogram car rounds a curve on a horizontal flat road of radius 50 meters at a speed of 15 meters per second, which is about 54 kilometers per hour. Will the car follow the curve or will it skid? Assume the pavement is dry and the coefficient of static friction is mu static equals zero point 0.6. B, assume the pavement is icy and the coefficient of static friction is 0.25. So let's do that example. This is example 514. What they've given us is M equals 1,000 kilograms. They're giving us that the R for the curve is 50.0 meters. I'm going to pretend like that 1,000 has 4 sig figs just by putting that decimal there. And I just added an extra sig fig to the R to make sure it's 3 sig figs. And the velocity, I'm also going to add a sig fig and I'm going to call that 15.0 meters per second. And my seconds always end up like some kind of weird fives or something. But anyways, that's what that is. And they want to know, will it skid? A, will it skid if mu substatic is equal to 0.600? Notice I add another digit. And then B, if mu substatic equals 0.250. Okay, again, I'm just making sure everything has 3 sig figs just to make the sig fig problem go away. All right, so I'm going to draw a free body diagram for this. Now, in reality, what's going on is we have a car like this. There's the headlights, and there's it. And of course, here's the road. And the car is in principle curving. And of course, the radius of the curve is R. And we've got that. So now I'm going to draw the actual free body diagram separate from the actual figure itself. And this is just like the radial axis again, or the radial direction again. I'm just going to call it X because we can. I'm going to treat the object as if it's a point particle, like I told you we're going to continue to do until we cover torque and center of mass. We know that there's going to be a normal force that acts in the positive y direction. I didn't label that y yet, but I should have. So here's my y. That's the normal force, F sub n. Now, we're also going to have a weight, which is mg. And in addition to that, since we're making a turn to the right, that means our acceleration has to be this way. So that's A sub c goes this way. And in fact, in order for that to happen, we have to have a friction force that pushes it that way. Okay. So we can now draw the friction force as pointing to the right and it's F sub static. And remember, solution F static is less than or equal to mu static times the normal force, but we also have the summation forces is equal to mass times acceleration, uh, and that's x or y. And we also have the centripetal acceleration is equal to v squared over r. So those are the equations we need. I can go ahead and write the summation of the forces in the y direction equals mass times acceleration in the y direction. Again, this is a flat curve. The car is going to maintain a constant y coordinate, so the acceleration in the y direction is equal to 0. And in this case, that gives us F normal, which points up, minus mg, which points down, is equal to 0. And that tells us that the normal force is just equal to mg. I'm going to call that asterisk. We're going to make use of that in a second. Now I've got the summation of the forces in the x direction equals mass times acceleration in the x direction. And in this case, we have the only force that's acting is the static friction force. So the static friction force is equal to mv squared over r. I'm going to call that equation 1. And what we'd say is the maximum friction force is F static is equal to mu static times the normal force, which would be mu static times m times g, which in this case is 0.600 times 1,000 kilograms times 9.80 meters per second, like that. And that gives us zero point 0.6 times 1,000 times 9.8 gives me 5,880 newtons. And that 0 is, of course, not a sig fig, it's a non sig fig, but we've got the uh, F static max. So that's the maximum force. Now, what matters is the velocity too big or too small to deal with that? So all I have to do is calculate mv squared over r, uh, and then to calculate, this is for part A, the maximum friction. So I should go ahead and label that A. So we've got that. So now I can calculate mv squared over r is equal to 1,000 kilograms times v, which is 15.0 meters per second quantity squared, divided by 50.0 meters. That gives me 1,000 times 15 squared divided by 50 gives me 4,500 newtons is mv squared over r. So in this case, for dry pavement, mu static is equal to 0.600. mv squared over r is less than fs max, implies no skid. So this is the answer to part A. Anybody have any questions on that? Now for part B, F static max is equal to mu static times F normal, which in this case is 0.250 times M times 9.80 meters per second, which equals 0.25 times 1000 times 9.8. This gives me 2,450 newtons. So F static max is less than mv squared over r implies vehicle will skid. And that's part B. Anybody have any questions on that? All right. So we've now figured out how to figure out whether or not something's skidding or not. I will tell you that the next thing is to design a curve, a banked curve, so that you don't need any friction to actually go around the curve. However, the downside of that is if you design it for that and then you go around that curve too slow, if you are actually going too slow and you really have no friction, then you're actually going to slide down the curve. And for instance, if you ever looked at exit ramps onto or on ramps, either one, to the interstate, on the side roads or whatever, you'll notice that they're always banked and they curve like this. And they normally curve around a deep hole or a pond or something like that. So obviously there'd be some negative ramifications if you happen to go too slow and slide down. But that's basically what's happening here. And what we want to do is example 515 for a car traveling with speed v around a curve r, determine a formula for the angle at which the road should be banked so that no friction is required. That's example 515. And part B is what is the angle for a road which has a curve of radius 50 meters with a design speed of 50 kilometers per hour. So this is example 515. Now, the formula, I've actually hinted it to you before already. Not that one. Not that one. This formula right here. You're going to see that has something to do with the banking angle of a curve. So just keep that in mind. Now, what we're saying is we want a velocity v for part A. Oops. Phi equals question mark for v being the velocity, r being the radius. And notice I'm not going to have an M. I'm not specifying the M, so we better hope that disappears. But not only that, we would expect it to disappear physically anyways, because if you'll notice when you go on an exit ramp to leave the interstate or an on ramp to enter the interstate, it'll have a speed limit of like 25 or 35 miles per hour, but it doesn't say a speed limit of 35 miles per hour for, Mack trucks and then the speed of 55 miles per hour for Volkswagen Beetles or anything like that. It has one speed and it works for all of them. So that's the reason for it. That's all part A. And then part B, they say phi equals question mark for v equals 50 kilometers per hour and r is equal to 50.0 meters. I'm going to pretend like both of those are three sig figs, so I'll go ahead and erase this real quick. So this is going to be 50.0 kilometers per hour. And that's what we're trying to figure out here. So let me start with drawing a diagram that we need. We're going to tilt the road at some angle phi. The car is going to be like this. There's your headlights, like that. And that's what we're actually looking for. Now, for a free body diagram, this is the case I've been warning you about. when you do a banked curve, that's the one time you don't want to use a tilted coordinate system. Okay, so I'm going to take my coordinate system and draw it perfectly normal. So I'm going to say X is to the right. I'm going to say Y is up. I'm going to say the car is a point particle of mass m, which hopefully will disappear. What we know though is that there's going to be a tilt to the road like this, and that tilt, of course, is an angle phi. We are going to have a force acting in the negative y direction. That's m times g. We're going to have a force acting perpendicular to the road. So in this case, I can't draw it green or red. It's going to be at that direction, and that's our normal force. Now, a little bit with the geometry here. Remember, the x-axis and this are supposed to be are both supposed to be parallel to each other. So this is like rebar going across a railroad track. So this angle is phi. That means this angle is also phi. Now, this angle right here is 90 degrees. So if this is phi, then this has to be 90 minus phi. And that means that since these two are 90, this must be phi. So there's the actual geometry part that we've got to figure out for this. Hopefully you followed that. Let me briefly go over it again. Parallel rays, this and this are alternate interior. So that's why this is phi. These two are complementary. So if this is phi, this is 90 minus phi. But these two angles are also complementary. So this is if this is 90 minus phi, this must be phi. So that's how I came up with that. Now I can break that up into a vertical positive component, which is Fn cosine phi. So that's the normal force times the cosine of phi. And then I'm gonna have a positive x component as well, and that one's Fn sine phi, like that. And we're imagining this without friction, so I don't have to draw any other forces. It's just this going on here. So let's go ahead and start with the summation of the forces in the y prime, or excuse me, in the y direction. Now all of a sudden I can say prime. Summation force in the y direction equals mass times acceleration in y direction. Of course, the acceleration in y direction is going to be zero, as we've been doing over and over and over again. So I'm going to get Fn cosine phi minus mg is equal to zero, and that tells us that Fn is actually equal to mg over cosine phi. I'll call that equation 1. Now I'm going to say the summation forces in the x direction equals mass times acceleration in the x direction. I've got to remember, of course, that the acceleration is going to be a sub c, and it's going in the positive direction. In this case, I have the normal force component in the x direction is supplying the force that makes me turn in the circle, so instead of friction. So now I'm going to say Fn sine phi is the positive force, and that's equal to mv squared over r. That's equation 2. So if I plug 1 into 2, I get mg over cosine phi times sine phi is equal to mv squared. Oops, that's an ugly squared. V squared over r. It's also a really ugly sign. You can see that the m's again cancel out, and you can see that sine over cosine is going to give me tangent. So, and I don't know why I wrote one of them theta and wrote the other one phi. Fix that. So what we get is the tangent of phi is equal to v squared over gr, so that phi is equal to the tangent inverse of v squared over gr. Now notice this is a little bit different, but notice what we had over here. We had tangent of gr over v squared. So you see it's actually the sort of reciprocal of the other formula, but that's the formula we're going to use. So we now have a formula for the angle. The angle has to be the inverse tangent of v squared over r. I will circle that or box it off and call that part A. And then part B, we want to work out what it is. So part B, we're going to say phi equals the tangent inverse of 50 kilometers per hour times 1 meter per second over 3.6 kilometers per hour. And then all that's got to be squared and then divided by 9.80 meters per second times 50.0 meters. And with this in mind, I get 50 divided by 3.6. And that gives me 13.89 meters per second. Now I'm going to square that. And I'm going to do 13.89 meters per second squared. And actually, I'm trying to fit in the inverse tangent in there now. So let me put this like that. Let me put this equals a little closer over here. And that's over 9.8 times 50 gives me 490. And that is meters squared per second squared. So I'm going to take the 13.89 squared and divide it by 4.9 times 10 to the 2. And that gives me the tangent inverse of 0.3937. And the inverse tangent of that is 21.49 degrees. So we'd say roughly phi is equal to about 21.5 degrees. Anybody have any questions on that? All right, we have now finished. I will provide you some information on the uh, projectile or on the drag force. So I might make a video or I might just point out a video, but you guys are free to go. Yes, yes, I can talk to you about that, Aiden. Y'all are free to go. Thanks for coming, everybody. Again, I'll wait for the last person to leave in case anybody has any questions. And this now makes twice that I've canceled that I've ended class. So sorry about forgetting that. Might help if I look at the hour instead of just the the minutes. But you have a good one, everybody. Thanks for coming, and have a great weekend. Stay safe and keep studying. Keep working towards your next face-to-face or your next online test as well as your online next face-to-face test. Have a good one.
Professor,
Yes, Grant. What's up?
uh, I've been trying to reach out to you. I missed the face-to-face test last Sunday,
Hmm.
and I was trying to just inform you. I had a little bit of a health issue, plus just irresponsible with my time. I was just making sure that you weren't going to drop me from the class.
No, actually, I've had a lot of things going on right now, so I'm feeling really generous. I've got like four people that missed the test. I'm going to work with y'all. It's just I had a lot of personal things going on right now that I
Okay.
have to deal with, so I'm a little bit behind. But I'll probably be sending you something tonight or tomorrow about that. But
Alrighty.
yeah, I'm going to let you make it up. It's not a big deal. But I and I'm going to do this. Though normally I don't let people make up face-to-face tests that when they miss them, but I'm definitely doing it this time because I've gotten behind from all my own personal issues. So I will
Yeah,
certainly work with you.
I just missed it because I was just irresponsible with time, and that yeah, I
That's
just wanted to make sure because I still want to be in the class. I just messed up, and
Yeah,
yeah.
it's not a problem. And like I said, there were some people, for instance, I listed as being due on I think it was June 7th or something like that, and then I made the actual time was actually 2 a.m. on June 8th. The reason being is I wanted them to be allowed to start it up to 11:59 p.m. And if they started at 11:59 p.m., they had to have 2 hours to take it. So I made it like that, and then some people saw it and said, "Oh crap, it's due 6/8. I got another day." But they didn't realize it was 2 a.m. So I've got a lot of things that are going on with that. I'm going to let everybody address that, and they'll have a chance to make it up. You get to do it with the Respondus lockdown browser and Respondus monitor. So as long as you have your own webcam and your computer can run Respondus lockdown browser and Respondus monitor, then you should be able to do it at your leisure. I'm probably going to just let y'all do it over the weekend or something like that, or maybe I'll send you an email and let everybody do it and have it be done by Monday for your class.
Alrighty, that sounds good. Thank you
All
so
right.
much.
Sorry about not getting back with you yet, Grant.
Oh no, it's fine. I was just worried I wasn't reaching out properly.
No, it
So
wasn't your
my
problem. I
bad.
did see some people were contacting me through Canvas, and I don't normally get those, so that was some of the problems. But again, no matter what, I'm still going to give you some leeway on this because I've dropped the ball with trying to keep up. Same thing with you, Aiden. I think you wanted to talk to me about the face-to-face test. I don't. I, you may or may not have missed one, but the same thing's going to happen with you. So,
Okay.
Okay, thank you. Yeah,
All
because I
right.
know Grant kind of answered the question for me, but I was out of town for a bit, and then the exam got pushed back over the weekend, and I work on the weekends to help pay for tuition. So it
yeah,
just the same thing with me, just with the timing and everything. I missed the exam too. But
no
it
problem.
sounds like my answer was already quite my question was already answered just
Yeah,
now.
and
So
there's actually, I think, like I said, I think there's two more people that missed it, and hopefully they'll see this video and hear that. But I'm slowly trying to catch up with my emails and all that stuff. So this is partly my fault. So I'm going to bite the bullet and help you guys too, even though maybe you missed it for not a good reason. I don't care. You're gonna be allowed to. Okay.
okay, thank you, Professor. I really appreciate that.
No problem, Aiden. Have a good one. Keep an eye out for your emails in case I send one to everybody. Like I said, there's a good chance it might be allowed back open this weekend, and maybe you'll have to do it on Saturday or Sunday or Monday or something.
Okay, all right, thank you. I'll stay on the lookout. I
All right.
appreciate it.
All right. Thanks, Aiden. Have a good day.
Thanks, you too. Bye bye.
Bye bye. All right. Well, thanks for coming, everybody. Have a good day. Bye bye.